experience a little bit with, let's say in special relativity, so you know what a metric is, but pretend that this time you don't really know what it is exactly. Okay? Okay, remember at the very beginning we speculated how would you create a space plus time metric. So we said, well, have some kind of space distance squared plus maybe time distance squared or something like that naively. We didn't know exactly how. When you're measuring distances in time, you can have some kind of a dt square in your metric. It won't be just dt squared. It'll be a function in front of dt squared, a function of r. And that function is basically the potential, the gravitational potential. That quantity which we call the gravitational potential, and it seems very prosaic and sometimes not even necessary, is just, makes things a little bit simpler to calculate in these silly problems of throwing, bullets down and shooting bullets and stuff like that, is actually space-time metric, meaning that it enters into that formula. You're going to have not just dt squared, you're going to have some function of r dt squared. Now, the metric of special relativity gives us several things. It tells us, for example, another thing that we need. Remember we spoke about the helix for a circular orbit, and then we said that it's kind of not really fair to draw this way, maybe it's like that, and so on. The scale factor was given by c, and that's in the special relativity metric, dx squared plus dy squared plus dz squared minus c squared dt squared. That c gives us the relationship between metrical time measures and space measures. Okay? Another thing that it gives us is the minus sign, which is very important. Another thing that it gives us is how you combine altogether spatial distances and time distances into an overall space-time distance. What we're going to see is that the space-time distance formula of special relativity, dx plus dy plus d squared minus dt squared, turns into something else, a little bit more general, a lot more general. And the hint as to what it turns into is given by exactly what we discovered now. Because what we expect now is that the time metric, the time-space metric, is going to be affected by what? By, let's say, the potential. The potential gives us a space-time metric. In the general situation of a curved space-time, you can have complicated stuff in it. In the simple case of the vacuum outside spherical symmetry, nothing rotating, right? Could be pulsating, but as long as it's maintaining spherical symmetry, in that kind of situation, what you'll find is in front of the dt squared will be a function which, for the cases that we're familiar with in Newtonian physics, moving slowly, like the Earth going around the sun or the moon going around the Earth, it'll boil down to basically just the potential, the gravitational potential. And you'll see something like, it looks like very strange. Why do you have a curved space-time where you have this metric, where in front of the dt squared you have a function, and of all things, that function is the gravitational potential? I mean, who would have imagined, right? But if you follow all these steps, you can see totally logically why that's the case. Again, in the limiting case, in a much more complicated case that Newtonian physics breaks down for, it's going to be something more complicated, and we'll get to those things. Okay?